All right, so in this video we are going to cover the preliminaries assignment, and so just some common things that we need to know before we can actually dive into the first couple outcomes. And so the first thing that we're going to look at are factors and prime factorization. And so the numbers that we'll be factoring are natural numbers, like 1, 2, 3, 4, 5, basically all of your counting numbers. So what a factor is to write a number as a product, which means to write a number as two numbers being multiplied to get to that same number. And so if we're looking at the number 12, 3 and 4 are factors of 12 because you can multiply them to get 12. So if you think about the number 12, 1 and 12 are also considered factors because they can multiply to get 12. 2 times 6, so 2 and 6 would be factors, and then of course the 3 and 4 that we were originally given. So anytime we're asked to factor something or to find the factorization, we're asked to rewrite something in a way where we have a product of two terms or two numbers, and that's where prime factorization is going to come in. So first we're going to find all of the factors of 19. And so if you're not good with your multiplication tables, you can use a calculator for this. You could take 19 divided by 2. Hopefully you notice that it is an odd number, so you're going to get a decimal. And so we would not consider a decimal to be a factor. We're not going to count this 9.5. You could take 19 divided by 3, 19 divided by 4, and you could go through all of the numbers, and you're not going to get any nice numbers. So the only factors of 19 are 1 and 19. 1 is always going to be a factor because we know that 1 times any number is itself. And so 1 and the number itself will always be factors, but beyond that, 19 is not going to have any other factors other than those two. So 48, we know that 1 and 48 are going to make sense. 48 is even, so you can divide it by 2. See, okay, 2 and 24 are also factors. You could take 48 divided by 3. So I get 3 and 16. You could take 48 divided by 4, and we get 4 and 12. Hopefully some of these you knew off the top of your head. I'm not going to take 48 divided by 5 because I know that 5 is not going to go into that because it doesn't end in a 5 or a 0. We can try 48 divided by 6, and I get 8. We can take 48 divided by 7. I get a decimal, so I know that 7 is not a factor. And then now I'm back to 48 divided by 8. Which we already know is 8 and 6. And so once you get back to factors that you've already found, you know that you've found them all. So the numbers 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48, these are all of the factors of 48. All right, so what we ran into with 19, that's called a prime number because it has exactly two different factors, itself and 1. And so that's what gives us a prime number. 7 is a prime number, 11 is a prime number, 4 is not prime because it has three different factors. 1, 4 itself, but then also 2. 18 is not prime, its factors are 1, 2, 3, 6, 9, and 18. And 1 is kind of a weird one. It is not prime because it does not have two different factors. It only has 1. So it's not 1 in itself because itself is 1. So 1 is just not prime, kind of a weird case there. Here's a list of some prime numbers 2 through 157. So if you want to keep this as a reference, that may help you figure out, instead of having to go through 103 and divide it by all the numbers you can think of, it is going to be prime. Now, if a number is not prime, we do call it a composite number. And so if it does have multiple factors, we call that composite. So every composite number can be factored into a product of prime numbers. So that's what we're going to look to next, prime factorization. That's kind of where we're headed. So we want to rewrite 12 as a product of prime numbers. And so you can do this in a couple different ways. And so usually how I like to do it is I like to make a tree. So I'm going to take 12 and I'm just going to break it down into any two factors that I can think of. So whatever comes to your mind first, however, 12 and 1 probably aren't going to be too helpful in this case. So I think of 3 and 4 immediately. Well, 3 is prime, so I can't break that down any further, but I do know that 4 is not prime, and I know that 2 times 2 will give me 4. So another way of writing 12 would be 3 times 2 times 2. 3 times 2 is 6, times 2 is 12. It's the same exact thing. 3 and 2 are prime, so this is considered the prime factorization of 12. Again, the word factor means to rewrite as a product. Prime means that all of the numbers in that product do not have any other factors other than itself and 1. So the next one, I can't see that number now, we want to find the prime factorization of 770. So again, that seems kind of daunting at first, but if you use this method where you can just break it down as you go, it does kind of help. So I'm going to start over here since this one's going to probably be a long one. And so right away looking at this, I think of 10 and 77. 10 and 77. So 10, pretty easy, 2 and 5. Both 2 and 5 are prime numbers, so I know that this part of the tree cannot be broken down any further. 77 can be broken down into 7 and 11. Both of those numbers are prime. And so again, you end up using the branches, the very, very bottom branches of this tree. And so our prime factorization for 770 will be 2 times 5 times 7 times 11. And you can make sure that this is right because when we multiply all of these factors, we should be given our original number, which was 770, so we know that we're correct. Next, we're going to look at least common multiples. So multiples are kind of like the opposite of a factor. And so multiples of 2 are numbers that 2 can go into evenly. So 2, 4, 6, 8, 10, 12, 14, 16. It's an infinite list. And so 2 through 16 are examples of multiples of the number 2. The reason why this works is 2 is 2 times 1. 4 is 2 times 2. 6 is 2 times 3. So clearly, since 2 is a factor of each of these, it's going to go into them evenly, which means that those are multiples. Multiples of 3 all have 3 as a factor. 3 times 1, 3 times 2, 3 times 3, 3 times 4, so on and so forth. So these are all multiples of 3. Okay, so when we're dealing with fractions, we need common multiples, and we're going to look at this more here in a bit. But if we were trying to find common multiples of 2 and 3, we could simply do this by making a list of all the multiples for 2, making a list for all the multiples of 3, and just simply looking at which ones they have in common. So 6, 12, 18, 24, 30. We obviously can't make this list forever, but they would have common multiples forever. So these are examples of common multiples because both 2 and 3 go into them. So 2 times 3, so you can see they both go into 6. 2 times 6 and 3 times 4. Since they are both factors of these numbers, they are common multiples. Okay, so we want to find least common multiples. We want to find the smallest one. So going back to this previous slide, yes, all of these are multiples, but when we're dealing with fractions, we want to keep our numbers as small as possible. And so all we would need to know is that 6 is a common multiple. Try to keep it as small as you can. That's where the L in LCM comes from, is least common multiple. So I want to find the least common multiple of 8 and 10, and we're going to use prime factorization for this one. But for these guys, we're just going to make a list. So I'm going to list my multiples of 8. So I have 8, 16, 24, 32, 40, 48, and I'll just go ahead and stop at 56. I may need to add some more. 10, and you may have thought when I was making this list, you already found it. 10, 20, 30, 40. We have a match. So the least common multiple between 10 and 40, or 10 and 8, is 40. And so we're done. Could we find more multiples? Yes, but the one that we're concerned with is the least common multiple. So we're going to continue this process, and now we want to find the least common multiple between 14 and 15. So I'm going to list the multiples of 14. So I have 14, 28, 42, 56, 70, 84, 98, 112, and I'm just going to go ahead and stop there for right now. Multiples of 15, we have 15, 30, 45, 60, 75, 90, 105, 120. Notice we still haven't found a match. And so we might not want to use this method every single time. With numbers like 8 and 10, worked out, we found 40 pretty quick. But with these numbers, we could be making this list for a long time and not find a match. So I'm going to skip this method, and we're going to use prime factorization to help us instead. So if I rewrite the prime factorization for 14, that would be 7 and 2. Those are both prime numbers, so that's the correct factorization for 14. For 15, it is 5 and 3. Notice they don't have any factors in common. So what that means is to find a multiple that they both go into, the smallest one is going to end up being the product of all of these numbers. 7 times 2 times 5 times 3. So if we figure out what that is, which it is 210, that ends up being the least common multiple. 7 times 2 times 5 times 3. So 210 would be our final answer here. Now we're going to use that same method here where we have 3 different numbers that we're looking at that we're trying to find the least common multiple between all of them. So we want to find the smallest number that they all go into evenly. So I'm going to start by breaking apart 18. Immediately I think of 2 and 9, which then I can go further into 3 and 3. So I have a 3, and a 2. 24, I think of 2 and 12. I think of 2 and 6, and then I think of 2 and 3. So the prime factorization is 2 times 2 times 2 times 3. Notice we're getting some duplicates here. They definitely have some factors in common. 36, think of 3 and 12. From here, I'm just going to do exactly what we did over here. 2 and 6, 2 and 3. So now with this one, since they didn't have any factors in common, we just took and we multiplied all of them together. Now for this one, they all share at least 1 2, and they all share at least 1 3. So we don't want to take 2 times 3 times 3 times 2 times 2 times 2 times 3 times 3 times 2 times 2 times 3. Our number would be a multiple, but it'd be too large, and we're looking for that least common multiple. So we want to find the prime factorization that has each of these covered. So I know for this first one I need a 2 times a 3 times a 3. For this one I need a 2, which I have, but I also need 2 more. So I need 1, 2, 3 2s, which I have, and 1 3, which I also have. So then this last one, I need 2 2s, which are covered, and 2 3s, which are also covered. And so the least common multiple is going to be the product of 2 times 3 times 3 times 2 times 2, which we could type into our calculator. And we end up getting 72. That is the number that all 3 of these numbers go into, and that is the smallest common multiple. You could verify that your number makes sense by taking 72 divided by 18. Yes, it's a multiple. 72 divided by 24. Yes, it's a multiple. 72 divided by 36. It also is a multiple, so we know that we correctly found the least common multiple. All right, so moving on. The reason why we want to know about least common multiples, or the reason why we need them, is when we're dealing with fractions. And so fractions a lot of times can be confusing because of what this bottom number means. And so when you think of a ninth, I want you to visualize a circle broken up into 9 pieces. This one piece represents 1/9. Think of it as an item. Well, the fraction 4/9, the top tells us how many of these pieces we have. So 1, 2, 3, 4/9 is shaded here. And again, here is a whole, and if you counted, there'd be 9/9, which is 1. So we chopped this pie, which was originally a whole, to 9 pieces, which is 1, but then we shaded just 4 of them. So 4/9 is represented by this red region here. Now, we want to write this as an equivalent fraction with 18 as the denominator. Oops, I did that wrong. I'm going to start with 4/9. And so you want to ask yourself, well, how do I go from 9 to 18? And the answer is double it. Now, if I double it and leave my numerator exactly the same, 4/18 is going to be very different than 4/9. Imagine taking your circle and chopping it into 18 pieces. That's going to make, and this is probably not going to turn out to be 18, but it's going to make each of those pieces smaller than the 9th. Think about if you had a pizza that you wanted to share with 9 people, you're going to get a lot more full than if you're filling it with 18 people. And so 4/9 is not equivalent to 4/18. You're going to be eating a lot less. So the trick is if you are changing the denominator, you need to make sure that you're changing the numerator by the same amount. And so to keep them equivalent, we would have 8/18. So we're going to eat the same amount of pizza, we're just eating smaller slices each time. And so you can see that these red regions are exactly the same size, they're equivalent, but we're just breaking it apart differently. So same idea, we have 14 over 21, and we want to write this as an equivalent fraction with 3 as the denominator. So notice our denominator is going to get smaller. Well, to go from 21 to 3, I need to divide by 7. And if you do something to the denominator, you have to do the same to the numerator. Otherwise, it changes the amount that you're representing. So if I divide both the numerator and denominator by 7, I end up getting 2/3. And again, in terms of pizza, or looking at this area model here, 1, 2 regions are shaded out of 3, which is the same exact region shaded 14 out of 21. Okay, so simplifying fractions, we want to do just that. We want to rewrite them to where the denominator is as small as it can be. And so you want to look between 30 and 42 and think of common factors that you could take out. So let's say you don't know your multiplication facts very well. You know that 30 and 42 are both even, so you could divide each of them by 2. Give yourself a starting point. You end up with 15 over 21. Now, even though that fraction is equivalent, 15 over 21 is not completely simplified. So then you could say, okay, what does 15 and 21 have in common? What factors? And the answer is 3. So you could divide them both by 3 and get 5 over 7. To make sure you didn't do anything wrong, you could take 5 divided by 7 to see what proportion that is, so about 71% of something. Then compare that to 30 divided by 42, where you can see we get the same exact decimal, so we know that we simplified that correctly. The next one, 15 out of 60, you may notice that 15 does go into 60 equally. Let's say you didn't realize that, you could start by dividing both by 5. And so 15 divided by 5 is 3. 60 divided by 5 is 12. Well, we can reduce this further because both have a 3 in common, 3 divided by 3 is 1. 12 divided by 3 is 4. So you may have fewer steps in the middle here. You might be able to get right to 1/4, and if you can, that's great. The next one, 325 and 650. Right away, I see that 25 would go into both. And so, let's see, 25 would go into this one 13 times, it looks like. And 25 would go into 650 26 times. 13 divided by 26 is 1/2. And you may have noticed that right away. 325 was half of 650. Okay, so now we're going to get into operations with fractions, multiplying, dividing, adding, and subtracting. And so each of these operations have very different rules, and you want to make sure that you keep them straight. Now, the first thing I want you to make note of is multiplying is the easiest operation with fractions. You can go with just your intuition. And so with multiplying fractions, we multiply straight across. So what I mean by that is we multiply numerator by numerator, denominator by denominator, and that's it. So we have 5 times 14, and so that will end up giving me 70. 7 times 20, that gives me 140. Well then, from here you are going to want to make sure that this is simplified, and if I remember right, I think your homework is kind of picky with that. So if it kicks back your answer, it may tell you, hey, it's not simplified, fix your answer. And so we will end up getting 1/2. And you could verify all of your work here if you have a calculator. You could use parentheses, take 5 divided by 7 times 14 divided by 20. So you get 0.5, which is indeed 1/2. Next one, same thing, multiply straight across the top, so 6 times 25, that will end up giving me 150. 5 times 12, that will give me 60. Notice that's not reduced right away. They both have an end in a 0, so I can rewrite it as 15 divided by 6. From here, they both have a 3 in common. Could divide both by 3, and I end up getting 5/2. Now, let's say you have a problem where there's a whole number. So let's say you have 3 times 2/7. Now, the number 3 represents 3 wholes. And so you could give it a denominator of a 1. And then that helps keep you organized. Multiply straight across the top, straight across the bottom. So I would end up getting 6/7 here. All right, so with dividing fractions, very, very similar to multiplying fractions, but you flip the second fraction and then multiply. So very similar, but we just have to rearrange our problem before we begin. And so I'm going to leave the 3/5 alone, flip, which is also called a reciprocal. So 10 over 12, and now it becomes a multiplication problem. 3 times 10 is 30, 5 times 12 is 60, which reduces to 1/2. Next one, 2/5 divided by 15/20. So again, leave that first fraction just how it is. Flip or find the reciprocal of the second, 20 over 15, change it to a multiplication problem. Straight across the top, we get 40. Straight across the bottom, we end up getting 65. So this is not, oops, I think 65 is wrong. Yep, 75 sounds better. From here, you can take a 5 out of both. So we end up getting 8 divided by 15, which is completely reduced. Now again, let's say you come up with a problem where you have a whole number. So let's say you have 2/7 divided by, we'll use 4. Well, flipping 4 may give you some issues because it doesn't have a denominator. So give it 1. So you can write this as 4 over 1. And so to rewrite this, that would be equivalent to 2/7 times 1 over 4. And now it becomes a multiplication problem. we get 2 over 28, which is the same as 1/14. And we're done. All right, moving right along, adding and subtracting like fractions. So what we mean by like fractions here is the same denominator. And having the same denominator is very convenient because it means that we're talking about the same type of item. So if I think of what 1/5 means, and this is not going to be even by any means, 1, 2, 3, 4, 5. So one of these represents 1/5. So if I have 2/5 added to another 2/5, it's easy to combine and see, well, that gives us 4/5. So you want to think of a fifth as an item. Think of it as the size of a slice of pizza. And so a lot of times students want to take and just add the numerators and add the denominators. Seems simple. That will give us 4/10, which reduces down to 2/5. Well, that doesn't make sense that if we had 2/5 of a pizza and added 2 more fifths of a pizza, that I would just be left with 2/5 of a pizza. We can clearly see that we have 4/5 when we add these together. Subtracting, so now that you've kind of seen the pattern, hopefully you could see, well, this would give me 3/6. So again, let's look at it in terms of pizza. So we have 6 pieces. So something like that, obviously it's not proportionate. And so we're starting with 4 slices. And we want to take away one of them. Well, that leaves me with 1, 2, 3, 6 of that pizza, which could be reduced to 1/2. So when your denominators are the same with adding and subtracting, it's not a problem. And so the rule is to keep the denominator the same. And then you can add or subtract, depending on your problem, within the numerators. So where this becomes an issue is when our denominators are not the same. So unlike fractions. So 3/4 plus 2/7. We already proved that adding across the top and adding across the bottom doesn't make sense here. And if you think about 1/4 of a pizza, it's talking about this size of a slice. And right here we're talking about 1/7 of a pizza. So 1, 2, 3, 4, 5. Nope, that's not even close. I'm going to try that one more time. 1, 2, 3, 4, 5, 6, 7. Much better. And so 1/7 is about that size. They're not the same type of thing. It'd be like trying to take 3 apples plus 2 bananas to get 5 apples. They're unlike things at this point, and so we can't combine them until we are talking about the same thing. So 4ths and 7ths, we need to figure out the smallest thing that they have in common, the least common multiple. And so that's where that was coming from. You may also hear this be called the least common denominator, because those are the numbers that we're looking at. So we need to find a number that 4 and 7 both go into, and we want to keep it small just to keep our numbers reasonable. And so you could list your multiples of 4, 4, 8, 12, 16, 20, 24, 28, list your multiples of 7, 7, 14, 21, 28. There we go. Our least common multiple is 28. So instead of thinking of these as 4ths and 7ths, we're going to turn them into 28ths. So to get 4 to become 28, I need to multiply by 7. And remember, if you do any alterations to the denominator, you have to do the same to the numerator. To get 7 to 28, we're going to multiply by 4, top and bottom. Now we have new equivalent fractions where our two fractions have the same exact denominator. So now we're ready to add them together. We add across the top, keep our denominator the same, and there's our new fraction. Cannot be reduced, so we don't need to worry about it. With our next problem, it's going to be a little bit easier because we're dealing with denominators of 5 and 10. And so I know that 5 goes into 10. So I'm going to leave this second fraction alone, and I'm just going to rewrite this first one. To make 5 become a 10, I need to multiply by 2. I'll also do that to the numerator. So I end up getting 6 over 10. Same denominator. Keep it the same. Subtract the numerators. That's going to give me a negative 1 over 10. Okay, two more examples. We have 40 and 14. So again, we define that least common multiple. We've done it in a couple different ways. We went through and made lists. We also looked at prime factorization. So I'm going to go ahead and do that. Break apart 40 into 4 and 10. Break apart 4 into 2 and 2. 10 into 2 and 5. I can break apart the 14 into 2 and 7. So we can see that they share a 2, so I know I need one of those. This one needs 3 2s, so I need 2 more. Also a 5. This one needs a 7. So my least common multiple, or my least common denominator, is 2 times 2 times 2 times 5 times 7. So I end up getting 280. That's how I'm going to rewrite both of my fractions. It's with a denominator of 280 before I can add them together. So I'm going to take 280 divided by 40 to figure out what I need to multiply to get it to turn into 280, which I typed in 240. There we go. And so I end up getting 7. So I'm going to multiply this one top and bottom by 7. So I get 21 over 280. I'm going to take 280 divided by 14. So I need to multiply this one top and bottom by 20. So I get 100 over 280. Now from here I can add the numerators together, where I get 121 divided by 280. And again, you may need to, in order for it to accept your answer, reduce this fraction. So you'd have to find what the numerator and denominator have in common and just try to make it as small as you can. For now, just to save time on this video, I'm going to leave it as that answer there. All right, last one, we're going to subtract. Last one on this side at least. I think we're close to being done. So 15 and 6, we can define what they have in common. Hopefully you can kind of just think it through so you don't have to do this side work every single time. So I know that they both have 30 as a common multiple and a least common multiple. I'm going to multiply this fraction by 2 top and bottom to get 14 thirtieths. I'm going to multiply this one by 5 top and bottom to get 25 thirtieths, and then we will subtract. And so from here, I will end up getting negative 11 over 30, and that is fully reduced, so we're done. All right, so the last one, blank slide, I just want to do a couple where we may run into some whole numbers. So let's say that we have 3 plus 2 sevenths. Again, we want to use that trick where we can treat this denominator as a 1 because it represents 3 wholes. Well, from here, the least common multiple between 1 and 7 is 7. So I'm going to multiply this by 7 top and bottom to get 21 sevenths, which would make sense because 21 divided by 7 is 3. Once you change that whole number to a fraction with the same denominator, same rules apply, keep the denominator the same, and add or subtract the numerators. So there's just one more problem you may run into, but this should get you started on the preliminaries assignment in my math lab.